Now let's take a look at 3.5, which is implicit differentiation. There's a little foxtrot, keep you happy. All right, so now let's talk about what the difference is. Implicit versus explicit functions. Okay, so explicit functions are the ones that we've been working with. Those are functions where you can actually solve for y. Implicit functions are where you cannot solve for y. So to give you a difference, if you have 2y is equal to x plus 4, to solve for y, divide everything by 2. So that would be 1/2 x plus 2. Now, with implicit functions, that's where you cannot solve for y. And that would look something like this. So if you had x, let's say x squared minus 2y to the third plus 4y equals 2, there's no way to, in that equation, separate the function so that you can solve for y. If you look at exploration on page 166, it talks about that. There are different ways to go ahead and graph it parametrically, or solve for x and then find the inverse and just think of the graph of the inverse of the inverse. But there's no way to get y by itself. And up to this point, if we can't get y by itself, then we don't know how to differentiate. Okay, so that's the difference between implicit and explicit. And so when we're talking about implicit differentiation, we're talking about differentiating functions like this, where you cannot isolate the variable for the function, which in this case is y. So now let's look down here and kind of talk about how these are different. On the left side, you have d over dx. Now you don't need, notice this is just d. Normally that would be y. Okay, normally that would be y. You don't have to have that there because sometimes y is not necessarily the function. Remember, it's this idea comes from the change in y over the change in x, which is y2 minus y1 over x2 minus x1, leading all the way back to algebra. So that all changes to, change in y over the change in x, delta y, delta x. Now sometimes, if the function variable, which is this y, because that's the function, if that changes, then you just leave it as d over dx. X is still your independent, and then whatever variable they use as your dependent is unknown depending on the problem. Okay, so again, this is your independent, but this is your dependent, your y variable here, which means it is your function itself. So they are very different. These variables that are used in your d over dx are important because this variable in the bottom, that's the one you're differentiating with respect to, because that's your independent variable. Okay, and we're going to talk about what that means as well. Now think about normally if you were to differentiate a simple function. So let's do y is equal to 2x squared minus x plus 1. When we find the derivative of this, it's just dy dx is equal to 4x minus 1. We haven't really thought about, well, why do we go from there to there? Okay, but the derivative of y is dy dx. Okay, so this is a change in y with respect to x. So if we had something like, to begin with, let's say 2y is equal to 2x squared minus x plus 1, we could choose to divide out that 2, or you can choose just to differentiate as it is, understanding that the derivative of y is dy dx. So then, and this is a constant multiple rule, so it's just going to be 2 times the derivative of y, which is dy dx is equal to 4x minus 1. And then you would divide out that 2 to get dy dx by itself. Okay, so the derivative of y is dy dx. So if you had something a little more complex, so let's say you had y squared is equal to 2x squared minus x plus 1. Let's say you had something like that. Well, you could take the square root of each side, right? Or you could differentiate both sides with respect to x in terms of y. So for example, this on the left side right here, that since y is a function, you will have to use what we just learned, the chain rule. Since y is a function, you will have to use the chain rule, meaning you're going to have to find the derivative of the outside. So this is the outside. And then your inside is your y. So the derivative of the outside, so d out, that is 2 times whatever that is to the first. And then your d in is just dy dx. Okay, so now when we find the derivative of this, it's going to be 2 times y, because you leave the baby alone, so this stayed the same. And now it's to the first power, so you can put that up there if you want to. It can be confusing because it could look like y prime, times dy dx is equal to 4x minus 1. All right, so now that's the derivative, but we have to solve for dy dx, so we're going to divide out that 2y. So when we do that, that gives us our derivative is equal to 4x minus 1 all over 2y. And then that is the equation for the derivative. Now, it might seem funny because we have in terms of y, but that is just fine because when we're asked to find the slope, they usually give us the point where they want us to find the slope, and we would just use the y point, the y coordinate, to plug in right there for y. Or if you wanted to, what you could do is up here, you could go ahead and solve for y. So up here, y would equal square root, positive negative square root of 2x squared minus x plus 1. And you would just put that in down there. Okay, but otherwise, when they give you the point, just plug the point in. Let's do an example. All right, so if we're finding the derivative here, these are the 4 steps that you need to follow. Number 1, differentiate both sides with respect to x, just like what we did, and I'll show you what that means further here. 2, collect the dy dx terms on the left side, or any side really. It doesn't matter, but the left side just makes more sense to our minds and to our eyes, but it doesn't really matter. Factor that dy dx out, and then divide by whatever's left over, or solve for dy dx. So let's try this. All right, so we're finding the derivative of this. Number 1, differentiate both sides. So y to the third is 3y squared times the derivative of y, which is dy dx. Because since y is your function, you have to differentiate it like that. Plus 2y times dy dx minus 5. And you have to do the dy dx here. That's very important. Because remember, with the chain rule, even though that's y to the 0 inside, the inside function, remember, that's y to the 0, the inside function didn't change. You still have times dy dx, or the derivative of y. Then minus 2x is equal to negative 4. So that's step 1. Step 2 is collect the dy dx's on the same side. So if we go through and identify our dy dx's, you have one here, here, and here. Now let's go ahead and keep those on this side, and we're going to get rid of this negative 2x by adding 2x. So you would have then 3y squared dy dx plus 2y dy dx minus 5 dy dx is equal to negative 4 plus 2x. They're all on the same side. And then step 3 would be to factor out. Okay, so all of these terms have a dy dx, so we're going to factor out a dy dx. Okay, so literally we are taking and dividing out a dy dx on this side. So that cancels here, here, and here. And now it becomes out front. So it's dy dx times what's left over. That is 3y squared plus 2y minus 5 is equal to negative 4 plus 2x. To make this a little bit more accurate as to what we're doing, you're factoring out a dy dx, but you're really multiplying it by dy dx over itself so it doesn't change the value. That's why this remains out front, and you're able to divide all of these by the dy dx. Okay, so now we factored it out. Last thing is to solve. So the last step is to divide out the 3y squared plus 2y minus 5. And you are left with negative 4 plus 2x all over 3y squared plus 2y minus 5. That is our final answer here. And at this point, if you have a value, x and y coordinates, you can go ahead and plug that in. All right, now that we know the steps, I want you to go ahead and try one on your own. Try x squared minus y squared equals 25, and then come back and see how you did. Okay, so let's see how you did here. First thing we do is we find the derivative of x squared is 2x, derivative of y squared is 2y times the derivative of y, which is dy dx. And then we get the dy dx term, that's this whole thing right here by itself. We divide out the negative 2y, and you get dy dx, once everything's simplified as far as it can go, is just x over y. And you can leave it in terms of y, that's just fine, unless otherwise specified. Okay, let's try another one. Now, this one has a given point. So when you find the derivative, so at this point right here, really at any point from here on, you could plug that in, whatever, or you could take it all the way to the end. It's entirely up to you. But go ahead and try this one. Okay, so let's walk through this kind of step by step. There's a lot of different steps here. Like I said, at any point beyond here, you could, beyond this first step, you could plug in negative 1 and 1, and then you would still have to get dy dx by itself. So I just went ahead and got dy dx by itself first. But I noticed when I found the derivative, every term, like this is one term because those two things are being multiplied, had a 3, so I could divide out a 3 out of both sides. So that's how I got down to here. But then I needed to get the dy dx terms on the same side, and that would be right here. I needed to get that somehow by itself. So what I had to do is I had to take this and distribute into there. So that's where these two terms down here came from, the x plus y quantity squared, and then the dy dx times x plus y quantity squared. Now let's get the terms with the dy dx by itself. That would be this term right here and this term right there. So then my next step is to get them on the left side. So I just got them on the left side by subtracting this. So right here I subtracted that from both sides, and then I subtracted x plus y quantity squared to both sides, and that's where I'm at now. And then the next step is to get dy dx, factor that out. And when you factor it out, you're left with negative y squared plus x plus the quantity of x plus y squared is equal to the right side. The right side hasn't changed. And then the last and final step is to divide that thing out. So here is your equation for the derivative. And again, leave y as y. That's just fine because for the point, they give us the point at x equals negative 1, y equals 1. So we're going to go ahead and plug x equals negative 1. So right there, and right there, and then y equals 1 into there, there, and there. And when you simplify that thing, it actually simplifies all the way down to negative 1. So then we're asked to find the slope of the point, find the find dy dx. So then that is dy dx. So that is the slope at -1, 1. Okay, so then this would be our final answer on that one. And let's go ahead and do one more, but now you're asked to find the equation of the tangent line. So you'll do what we did above, but go one step further. Now that you have the slope, find the equation of the tangent line. Go ahead and pause the video and try this one on your own. Okay, so let's take a look at this kind of step by step. First thing, you just find the derivative. Implicitly, the tricky part is right here. We haven't done one like this, but you have to use the product rule. So what I did is I did the derivative of x times the derivative of y plus, sorry, the other way around. X times the derivative of y plus the derivative of x times y. And then over here, you have 2y times the derivative of y, dy dx. Okay, and the derivative of a constant, that's where that 0 comes from. Now the next thing is you have to get dy dx by itself. And so what I did is I took this term and subtracted them over to the other side. Also, what I like to do is you notice how in this term and this term, the dy dx is on the right side. I just flip them around. So right there, right there. It's a little easier for me to visualize when I take out that dy dx, what's remaining, the x plus 2y, and then divide out that x plus 2y, and you get, here is your equation for the derivative. Now at this point, we're going to go ahead and plug in those values. So x is 2, y is 0, so that we're going to go ahead and plug 0 in there for y, and then 2 in there for x, and when you simplify that down, you get just -2. Now, we have to go one step further and find the equation for the tangent line. Remember, all we need is a point and a slope, and we have both of those. We have the slope, we have the point, so we plug it into the point-slope form, and we simplify down to just y, and then this is our final answer. So I'm going to highlight this as red as well. That is our final answer. That's what they're asking us for. And that will do it for 3.5 implicit differentiation.